Alright, here we go with iChem lesson 25 on heating and cooling curves. Actually, specifically, we're mostly going to talk about heating curves, but all of these concepts can be applied to cooling curves as well. So first, let's talk about just some basic heat flow and physical changes. So phase changes involve a flow of heat that can be it should more say calculated than measured. An endothermic process, just like an endothermic reaction, is a heating, adding of heat type process. So in terms of physical changes that a substance can undergo, you can go from solid to liquid through heating and liquid to gas through heating. And those are called melting and evaporation. And another word for evaporation, when we're talking about water, a lot of times we say boiling. Endothermic processes are the opposite, that energy is released or removed, so these are cooling processes. Gas to liquid and then liquid to solid all happen upon cooling. So gas to liquid, that would be our condensation, and liquid to solid would be our freezing. So we can represent these as a curve. So notice the y-axis here is temperature. You should be drawing this curve on your viewing guide. So draw the y-axis, label it temperature. The x-axis, you can label it time. I often sometimes just leave the label of the x-axis blank. These processes do happen over time, but I don't know, I just leave that one blank. Anyway, and so you can kind of see at lower temperatures, and this is the heating curve of water, so less than the melting point, 0 degrees, water is a solid. Upon heating, that solid will increase in temperature until it hits the melting point, and then it will melt at constant temperature. And you guys saw this in your experiment in class today. You should have noticed that in your mixture of ice water, you started here out on this line. You had a mixture of solid and liquid. As you added heat, at first, the temperature did not change. The only thing you should have observed here was that you're having fewer and fewer ice cubes. Then when all of the ice cubes are gone, you start to observe an increase in temperature. This only happens when the process of the change in temperature only happens when the process of melting is over. Then increase in temperature as a liquid until you reach the boiling point, and then you have a mixture of liquid and gas until all the liquid is gone, and then you have gas increasing temperature. So to kind of conceptually describe what's happening at each phase, you should have the pieces labeled on your graph, and now here we're going to describe it. The solid, heat causes the particles to increase in speed, which changes their temperature. Okay? Remember, temperature is a measure of kinetic energy. So really, when you're seeing an increase in temperature, you're measuring an increase in speed. And then melting, we're not changing the temperature anymore. The heat causes the intermolecular forces to weaken. The molecules aren't moving any faster, but the forces between the molecules are becoming weaker. And then we go from when melting is done, when we have all liquid, the heat will cause the particles to increase in speed and change the temperature until you get to the point where the intermolecular forces break again. So at boiling, heat causes the intermolecular forces to break. There is no change in temperature. And then finally, in gas, heat causes the particles to increase in speed, and there is a change in temperature. The main points in each of these parts is the idea that when you are undergoing a physical change, like melting and boiling, there is no change in temperature. When you are staying a single phase and adding heat, then the temperature changes. So, in terms of calculations, there are two equations we'll use here. Our same old friend, Q equals mc delta T, where m is mass, C is specific heat, and delta T is the change in temperature. And then a new equation, Q equals mole times delta H. This is for a phase change, where the temperature is not changing. You have moles and delta H. So you must be able to recognize whether you're undergoing a phase change or a temperature change, so you can decide which equation to use. So let's summarize them and kind of putting it all on like the idea of looking at the graph. If you look at the graph and look at the diagonal lines, on the diagonal lines they show the fact that there's a slope shows you that there's a change in temperature. Here you would use the equation Q equals mc delta T. The plateaus, the fact that they're flat, shows you that there is no change in temperature. Then you would use the equation Q equals mole times delta H. So now let's apply this all to figure out how much heat is required to take a 50-gram sample of water and heat it from -40 degrees Celsius to 140 degrees Celsius. So if I'm looking at my heating curve again, that's taking it from way down here and heating it to way up here. This is the extremes of the curve. So if we look at what's happening to go from point A to point B, you would go first, we'll call this segment 1, you would be a solid heating from -degrees to 0. In segment, let's call it segment 2, you would be melting. In segment 3, you're going from a cold liquid to a hot liquid, changing temperature. Finally, you reach the boiling point, and now you're a liquid boiling. And then once you're all gas, you're a gas heating up. So really there are 5 segments, 5 pieces to this calculation. In segment number 1, again, let's reiterate. You're going from -40 degrees Celsius to 0 degrees. That's a change in temperature. So I'm using Q equals mc delta T. Let's plug in what we know. M is 5 grams. Now be careful here. C, I don't want to use the C of water when I'm talking about ice. I want to use the C of ice. So 2.1. I got that from, you have to be given, these are on page 5 of your practice packet. The specific heat of ice is 2.1. And then the change in temperature, final minus initial. The final temperature of this phase, this segment, is 0 degrees, heating to the melting point. The initial temperature minus the initial temperature is -40. So I end up with 5 times 2.1 times 40, which gives me 420 joules. The unit here comes from the unit of energy in my constant. Okay, now next step, segment 2. I'm going from solid to liquid and not changing temperature. This equation is Q equals mole delta H. Notice I have 2 delta H's given to me here. One of these, I know it's hard to read on here, but your paper should be a little bit clearer. This says vape. This says FUS for fusion. This melting, if you want to label it, that's where you use FUS. Boiling, that's where you use vape for vaporization. So here I'm going to use delta H of fusion. Now I just plug it in. Now look here, now I need moles. So here's where this hint at the top comes into play. Anytime you see that when you're doing the calculations, when you cross one of these plateaus, you're going to need to calculate moles. So I'm going to go ahead and calculate moles up here. We really should have done that first. So I have 5 grams of water, and I want to know moles of water. So grams to mole, divide by molar mass, the molar mass of water. 2 hydrogens, 1 oxygen, 18 grams per 1 mole. I get 0.28 moles of water. I need the moles whenever I'm at a plateau. So here Q equals 0.28 times 6.01. I plug this in and I end up with 1.68. This is in kilojoules. Now in the end, what I'm going to have to do is add all of these numbers together. So I want to make sure they're all in the same unit. This is in kilojoules and that's in joules, so I can't add them all together very easily. So I'm going to multiply this by 1,000 to get everything into joules. So I actually have 1,680 joules. Okay, segment 3. I'm going from a liquid at 0 degrees to a liquid at 100 degrees. I'm changing temperature. So Q equals mc delta T. Plug it all in. Q equals M, which is mass, times C now. Now I have liquid water, so I can use the 4.18 that we've been using, times delta T. Final will be your boiling point, which is 100 degrees. And your initial will be your where you started in this segment when you were done melting, which is 0 degrees. If I plug all of this in, I end up with 2,090 joules. All right, 2 more segments to go. Segment 4. Now I'm here. I'm a liquid becoming a solid and no change in temperature. Q equals mole delta H. And here, boiling, I use the delta H of vaporization. Now plug it in. Q equals moles, which we calculated to be 0.28, times delta H of vaporization, which we're given down here as 40.7. I plug this in and I get 11.40. Remember, this is kilojoules. So when I need to add them together, I need them all in the same unit, so I'm going to multiply by 1,000 to get 11,400 joules. All right, last segment before we add them all together. Segment 5. It's all a gas. And I'm going from a gas at 100 degrees to a gas at 140 degrees. Q equals mc delta T. Plug it all in. Q equals M, which is mass, given as 5 grams. C, now I want to use the C of water vapor, which is 1.7. And I want to use delta T. Now the final temperature is 140. And the initial temperature is where I ended my boiling, which is 100 degrees. I end up with here 340 joules. Now I need to add all of this back, add all of this together. 420 plus 1,680 plus 2,090 plus 11,400 plus 340. I end up with a total of 15,930 joules. If I want to now, I can go back and convert this to kilojoules by dividing by 1,000. Either one of these is an appropriate answer to the question. If it asks you for a specific unit, just pay attention.